Hello. Today I interview Patrick Mineault, who is this amazing researcher in the field of NeuroAI, which is the intersection of neuroscience and artificial intelligence. And this has been kind of a theme of this podcast, is like trying to understand, the intersection of those two fields, how the brain works and how AI works, and what they can learn from each other. And so Patrick is just full on deep in that world, and he's I think the crucial bit, which is really curious and exciting today, is we chat about a recent piece they wrote on with brains on demand, which is this idea that as we get better and better at modeling for AI to model the brain, that we're going to be able to just kind of like have this downloadable click brain on demand, and that thing will use it for testing content. We'll use it for testing health interventions. We'll use it for all those kinds of things. And long term, that will be hopefully good for humanity to be able to test things and how their impact on us without necessarily using humans. And so there's obviously some negatives to that too, but I think it's really cool to see Patrick's perspective on how we'll create these brains on demand and how they'll be used. So with that, thanks for listening as always, and enjoy the episode today with Patrick. Bye. Hello, Rhys's Pieces. I'm Rhys, the co-founder of Root, and welcome to The Rhys Show. This century is a turning point in human history, and I'm here to help you navigate it. I hope you come away with a new understanding of the scientific, technological, and societal trends that are poised to radically reshape our world, and how you can work with those trends to become a live player in building a solarpunk future. And today, I'm excited to chat with Patrick Mineault. Patrick is a neuroscientist and AI researcher. He's been a data scientist at Google and a research scientist for brain-computer interfaces at Facebook, and he's really concentrated on NeuroAI, this intersection between AI and the brain. Patrick, thanks for being on the show and welcome.
Oh, thank you.
Yeah, excited to dive in. And I think, Patrick has a couple brilliant pieces on his website and X-Core Consulting about just this intersection of neuro AI. And so the goal for the listeners today is to kind of help you all understand like how we're using the brain to understand AI, and also more recently how we're using the AI to understand the brain, and then finally how that will impact our daily lives. So with that, I kind of want to start, Patrick, and say like, what has been the history of neuro AI? What is it, and what has been like the history of the field?
Oh, yeah, absolutely. So it's a fascinating history, and these two fields have always been intertwined with each other. So, and the example I like to give to people is NeurIPS, which is the most famous, the biggest conference in artificial intelligence, is Neural Information Processing Systems. It's actually a neuroscience and artificial intelligence conference at the start. But right now it's blown up to be essentially 95% artificial intelligence, and there's just a tiny bit of neuroscience in it. But from the very early inklings of these ideas about artificial intelligence, people have been inspired by questions about the brain. So we can talk about the perceptron, which was this invention of a simple, linear feature detector followed by a threshold function, which was inspired by these studies of how neurons integrate their inputs and fire up after a threshold. But I think the most famous example is really that of convolutional neural networks. So in the 50s and 60s, these two folks at Harvard Medical School, David Hubel and Torsten Wiesel, did some really seminal studies in the visual cortex. So they were the first to put an electrode in visual cortex and to figure out what neurons do there. It seems like vision is really this this seamless thing to us. It just happens naturally. I look at your face and I'm like, oh, that's Rhys. But it's a complicated series of computations that happen inside the brain. And at the time, we really had no idea how this, this ability to recognize people in different lightings and different conditions, maybe even like somebody that you haven't seen in 10 years, like you still recognize them even though they've aged, and maybe they have a belly and, and so on and so forth. So nobody really knew how that actually worked in the brain. And so they were able to show that you have these neurons in primary visual cortex, which we call the simple and the complex cells. So the simple cells essentially integrate information directly from the eye and essentially make out patterns of, let's say, light and dark. And so they're able to determine whether, for instance, there's a bar that's like a dark bar that's moving in the visual field in a given spot. And they were also able to find these other neurons, which were called the complex cells. And so these complex cells are able to detect, let's say, dark bars, white bars, dark light edges or light dark edges. So all these combinations thereof, as long as they have the same orientation in a given spot in the visual field. And so what they inferred from the fact that you have these two kinds of neurons is that, one of them must be fed into the other. So there was kind of this hierarchical computation that was happening where you have this selectivity operation, which is followed by a pooling operation, they call it. And so later on, people, looked at this, and this was like very interesting. They were trying to do visual recognition in computers, and they were inspired by this research to create first the neocognitron, which was Fukushima in Japan in the late 70s, and later the convolutional neural nets. We're talking about Lynette and Jan LeCun, who worked on this stuff in the late 80s and early 90s. And so what we really added to the mix is the ability to essentially instantiate this idea of selectivity and pooling, and then selectivity and then pooling, and selectivity and pooling. And what if you add backprop to that so that you can actually train the weights in a way that would allow you to solve a task? So the task in this case was recognizing digits, and that was the famous, inspired by the famous MNIST task, but was actually used in the end by the United States Postal Service for recognizing zip codes that were written by hand back in the day.
Yeah.
And so that, eventually inspired the modern deep learning revolution. That famous moment in 2012 where that team at the University of Toronto with Jeff Hinton and Alex Krzyzewski were able to completely trounce the competition in solving ImageNet. Did something like 25% better than state of the art, and show that, like, hey, this thing that we have now, CNNs, it's not a toy. Like, deep learning has arrived, so you better watch out.
Yeah.
And so we've seen like this kind of like crosstalk in between these two fields. Like, wow, isn't it incredible? First of all, like, let's just stop for a second, and to think that something which is inspired by the brain, you could instantiate in the computer, and then you could do the kinds of things that humans can do. I mean, it's incredible that this is possible at all.
Yeah, I love that. I think I love it's like, it is crazy that, we take it for granted, but obviously 50 years ago or 100 years ago, if you said, 100 years ago, definitely, but even 50 years ago, if you said, hey, these random new little computer things that are popping up, we'll be able to use them to actually do USPS zip codes, and they'll be able to look at all these letters and numbers and like to actually determine what they are. It's like, wow, that is and it's cool to hear also like the NeurIPS. I never thought that NeurIPS was a combination of neural stuff and then AI stuff. It's interesting too, because I think there's like the selectivity and then the pooling in the CNNs, the convolutional neural networks. I imagine kind of a CNN. There's recurrent neural networks, and then there's convolutional neural networks. Is that right? And are the CNNs, do they both have like, and I guess there's just like pure ones. There's CNNs, there's RNNs, and then there's ones that like don't do any, or what's the difference between CNNs and RNNs?
Yeah, and then there's transformers, I think,
And
is
then
the third one that you're
transformers,
thinking about.
Yeah.
Yeah. So it's interesting because these kinds of architectures were really, set up to solve different kinds of problems. So, when RNNs came about, really the kinds of problems that people were interested in solving were things about time series, for instance. So it would make a lot of sense that you would look over a big window of time and, figure out what happened in the past, and then somehow find like a good representation to accumulate all of this stuff over time, and then do predictions based off of that in kind of a recurrent manner. But interestingly now, neuroscientists are using these different kinds of neural networks to model different parts of the brains. And so, which I think comes down to like just some models are kind of more diffeomorphic or like slightly more isomorphic to certain parts of the brains than others. And so, if you'd like, I can get into that.
Yeah. Let's do that in a second. But I think so. It sounds like there's a yes. So there's like and it's the ability to do the selectivity and the pooling, where you have selectivity, which is the that's like determining whether that's I think of it as like maybe a simple feature detector or whatever, where you have like a line like this and then a line like this, and you're able to determine whether the thing is the neuron is able to be like, oh, is this like a horizontal line or a vertical line? And then the pooling is where you like take those into aggregation and say like that's an eye, and then you take and then that eye then gets pushed over to the selectivity side, where it's like we have an eye, now it's like combine that with some other stuff to then do some more pooling. Is that how selectivity and pooling kind of co-evolve, or how does that work?
Yeah. So you can think about a real situation in which you'd like to have information which is invariant to the sign of the edge. So I have a dark IKEA bookshelf behind me. And so if I place my hand, in front of this bookshelf, I'm going to see the outline of my hand. And so that outline, as you can see, the top, my top fingers, I can see, a dark pattern at the top and a light pattern at the bottom. But, if I just, change things this way, I get the opposite pattern. Or if my fingers are against, a white book, which is in the back, then I get the opposite pattern, right? And yet my hand still exists in all these cases. Like what I really want is like a way to detect that this hand, my fingertips, exist. And because these are real edges which are defined by differences in depth, right? So these are like what you might call intrinsic edges. So they're not going to go away. And so they might be very useful for recognition. And so what I'd like is essentially to be able to detect the presence or absence of this edge, regardless of whether the contrast is positive or the contrast is negative, right? Whereas a more basic feature detector would really only work with one kind of lighting or like one kind of arrangement of the thing that you're trying to detect against a background. And that's intrinsically less robust. Like I said, you can do recognition of a familiar face, whether that familiar face is so I'm Canadian, so I'm going to use like seasons-based metaphors. Obviously, this is not going to work as well in California. But if you meet them in the winter, they're going to be against like a very white background, presumably, or maybe like a slushy background if it's the shoulder seasons. If you meet them in the fall, it's going to be like maybe against like these like red leaves. And it's going to be very different again in the summer, and yet people's identities don't change. So it's this like fundamental problem that you want to solve. You want to be able to recognize things in an invariant fashion, despite the fact that the world keeps changing and what it is to be a thing can change. So if you just look at the raw patterns that fall on your eye, they're just like hopelessly entangled with all of these external causes of variation, which don't matter in the end for the recognition.
Yeah, that's interesting. And so is what is it? So selectivity. So like, what is the selectivity side and what is the pooling side? What do those words like mean?
Yeah, absolutely. So the selectivity is to say, so for instance, I have a pattern of light against dark in a horizontal arrangement, right? So one's on top of the other. So that's a selectivity operation. The way that you can do that is basically you get a bunch of neurons which light up or have positive responses when they see light at the top and positive responses when they see dark at the bottom, for instance, right? And then you can add to that a threshold operation. So the threshold operation is also inspired by the operation of the brain, which has, neurons, when you put electricity in them, they don't do anything until you reach like a certain threshold of activation. And when they reach that threshold of activation, they have this instantaneous or kind of instantaneous response, which is called a spike or an action potential that then propagates down the axon. But the important thing is that there's a threshold, and so anything below that doesn't cause an activation, and anything above that causes an activation. There's a small zone in which things are a little bit stochastic, and you can combine this selectivity for like this specific set of patterns with a certain threshold. So, you only fire like whenever there's a certain amount of the stuff that you're looking for. And then you say like, this pattern is okay, but this other pattern, which is the exact inverse, that's also okay, right? So then you can add that in. And this third pattern, which is kind of the same but slightly different, that also counts. And this fourth pattern, and so forth. And so with that, you can accumulate inside of this neuron like this ability to respond to a lot of different patterns which correspond to the same thing.
Great. And so that's the pooling side.
That's the pooling side.
Okay,
and
great,
so
great.
Maybe there's another like metaphor which I think is pretty useful, which is when you reach like high level cortex, you have these neurons which respond to whole parts of faces, right, or even like whole faces. And so maybe the way that you want to generate a neuron, which is the Patrick neuron, is maybe there's a lower level neuron that just responds to Patrick's profile, and then Patrick 15 degrees looking to the right, and 30 degrees looking to the right, and 100% like looking to the right, and essentially like just stitch all of these different views of the same person together until you're selective for Patrick in any sort of head rotation position.
Yeah, love it. Love it. That's great. Yeah. And thank you for just like, double clicking on that where it's like, you have the selectivity for any given pattern. Like, oh, great. I'm seeing Patrick. This is Patrick in the front. This is Patrick 90 degrees. This is Patrick 90 degrees the other way. Okay, cool. We can pool those all together to get a meta neuron or whatever. That's like, oh, this is like the Patrick neuron. And so that, boom, we get Patrick. Okay, that makes sense. And so, and the cool thing I think is that, we had for so long, we were doing, I want to kind of, go to like the middle part of the story now, where it's like, we have this history obviously of like, of AI and kind of like pulling AI, starting to pull these ideas from the brain. But now what we're doing is it feels like we're kind of going the other way, where AI is kind of, where we're like using AI to learn about the brain, or using AI to kind of model the brain. And so you call this like brains on demand. You could call it like brains as a service. So tell us more like,
that's much better, because that spells out BAS, right?
BAS, baby.
Absolutely.
And so tell us more about this. What is a brain on demand or brain as a service? How does this work?
Yeah. So, of course, these some neural network, artificial neural network architectures were really inspired by the architecture of the brain, and so eventually people like came around and said like, wait, are these actually like the brain? And so the way that they looked at this was the seminal research in this field was done around 2014. So 2 years after this ImageNet moment, there were some inklings that actually these networks that we trained in silico to solve these tasks with pictures and bits and computers, they were actually a lot more like the brain than we originally gave them credit for. So, originally we were like, well, maybe we're just like thinking about these as metaphors for the brains, and they turned out to be good because they have compositionality, which is very important for artificial intelligence, but maybe they're not really like the brain. So the surprising thing is that the TLDR is that they are kind of like the brain in really interesting ways. And so maybe the first thing to get out there is like, how do you even compare a brain and a neural network? Those two things don't seem like they should be comparable in any sort of meaningful way. And so the technique that people have used over the years is to use a battery of stimuli. So if I present to you like 1,000 different stimuli, I can measure from your brain, from your visual cortex, your early visual cortex, intermediate visual cortex, infratemporal cortex, your hippocampus, whatever, using MRI, ECOG, single electrode recordings. There's a lot of different ways that you can record information from the brain. And I can get like a big basically like a big matrix of responses, right? So one vector per image corresponding to different neurons, different voxels, um, different measurements, and then I can do exactly the same to a neural network. I can just present, quote unquote, to this neural network. Here is a series of images. What is
There's
your
all these
response?
cats, you know. Yeah.
Yeah. So the important thing here is that we're not necessarily interested in the last part of the neural network. So as you know, something like a modern deep neural network is deep because it has a lot of layers. And so what we usually care about is the intermediate layers. Because the last layer is not so interesting. It just, pushes it onto different classes, like this kind of dog versus that kind of dog. But the intermediate layers are where, quote unquote, the real action is. And so with this, we get basically two matrices corresponding to the responses of the brain to a battery of stimuli, the responses of an artificial neural network to this battery of stimuli, and we can compare them. And lo and behold, we see like really interesting things pop out. So the first thing is that, you can try like an untrained network versus a trained network. And a trained network looks more like the brain. You can try networks which are better at solving the task, which are better at ImageNet versus networks which are worse at ImageNet. And those that are better at the task that humans can do also happen to be more brain-like. At least it was the case up to about 5 years ago. I should say, because there's people that are going to be yelling in the comments. We can look at the hierarchy. So the brain has this, the visual cortex has this amazing organization where it's really organized in these layers and these areas which project onto one another. So you would think that, the way that this works is you go from the retina to the thalamus, and then eventually the primary visual cortex to V2, V4, and then different subparts of inferotemporal cortex, area IT. And so you can look at a deep neural network to see like, okay, well, does V1 correspond more to lower lower layers of this artificial neural net? What about V2? What about V4? What about IT? And what you see is a real recapitulation of what happens inside of the visual cortex. So the lower layers of this artificial neural network correspond to lower layers of this deep neural network, which is of this brain. So it just seems like it's the smoking gun.
Yeah.
Oh wow, these things are really like kind of like each other in a much deeper way that we had anticipated originally.
Yeah, I mean that's great. It's an interesting. It's also cool to know. I love talking with researcher types because you're always like, hey, here's this 2012 paper was the original kind of deep learning Hinton paper or whatever, and then in 2014 was this original paper. So you just knowing the dates and the titles of the authors is just like classic, and I like that. It's also interesting. I mean, it is crazy in thinking about, and just for the listeners, it's like you have obviously these V1, V2, V4 things are these different like hierarchical like deep layers of the brain where you have these like cortical columns or whatever that fire on different things. And so and what Patrick is saying is that there's that kind of evolved thing within our biological environment where our brain, because the world has hierarchy in it, so you're kind of our brain then like was like, oh, there's hierarchy, I can be hierarchical as a brain. And then similarly, if you're an AI and you're trying to like determine stuff and you're trying to be an image netter or whatever, and you're trying to like look at and determine cats, it makes sense that you would like have these different hierarchical layers in order to do that. So that is, I mean, it makes sense. It's also kind of crazy that there's this convergent evolution.
It makes sense with hindsight.
Yeah. Oh, totally. Oh, totally.
Yeah.
And so
100% hindsight.
Yeah. Oh, yeah, exactly. Because it also would totally make sense if it was some random other crazy AI way. But so do you think, so we have these, so we were able to match them to each other. And we're able to like say, hey, there's this like new neural net that kind of looks like a brain. And so tell us like what, like, I guess a couple questions here. I guess the first is tell us what we can do with these or I guess actually my first question is how close is this thing actually to a brain yet? Like we have this idea of like, oh, we can just like create these like brains and like push them around the world and they'll be able to like trigger on stimuli and stuff like that. But are we actually close to this right now? Or like how close are these brains to being like real brains,
So not very, but and I'll qualify by not very. But I think that we have to look at the general trajectory of these models, and maybe we can compare it to, for instance, like DALI 1. DALI 1 didn't work very well. If you look at the original post from OpenAI, so DALI is, of course, a generative AI that can generate like whatever kind of image that you want based off of a text prompt. Um, it the original versions didn't work very well. Even like 2 years ago, just the fusion models didn't work very well, and now we're at the point where we've reached a point where I personally just use DALI to generate images in my blog post. I've forgotten how to use Photoshop if I ever did know how to use it. So there can be like a very fast trajectory that comes from scaling current approaches to larger data sets or more brain areas in our case. So that's kind of my caveat. But I do realize that these artificial neural networks are not really like brains. So there's a bunch of little things. There's a bunch of big things that we can say about them. So, for instance, brains have this special rule that there's positive neurons and negative neurons. There's excitatory neurons, which have certain patterns of connection, and then there's inhibitory neurons, which have certain patterns of connections. And they have to be wired up in special ways inside the brain. And artificial neural networks don't have those kinds of constraints. So that's called Dale's law. But if we wanted to, we could create an artificial neural network which embodies Dale's law, and is written up in this particular way. It's just that we haven't found it to be useful for industrial applications of AI. And so if we wanted, we could do that. We could add topography. You were talking about recurrence. So we know that the visual cortex has recurrence, right? So it's not that there's just a feed-forward pass from my eye to my thalamus to the visual cortex, to the primary visual cortex, is that there's recurrent activity in the primary visual cortex that happens over time. And then even talk from the highest level parts of the visual cortex down to the primary visual cortex, right? So we have these very simplified systems diagrams that we, canonically use in the field of NeuroAI that we know are not like really realistic if we look from the anatomy. But these things can be fixed. There's no like a priori reason why you're like, oh, well, this approach can't possibly work ever because you don't have these things. It's more like we're adding like a little bit more, meat on the bone, so to speak, of these models, which are originally just metaphors for the brain. But if we keep adding more and more biological reality, they will become ever more brain-like. So they're not very realistic, but the devil's in the details. And there's probably like 7 or 8 different low-hanging fruit that we can use. And I list them, I think, in my blog post that we can use to make them more biologically realistic.
Yeah, great. Yeah, and as a note for folks, there's the blog post that that Patrick is referencing is there's one on A16Z's future, which is AI's next frontier, brains on demand, and then there's one on his website too, the what's the end game of NeuroAI at xcorr.net. And so I'll link both of those in the show notes. And they're both very excellent. It is so. Is there Patrick? Is there like a Yeah, so what I'm hearing is there are these pieces. And when I was chatting with someone who works at one of the random NeuroAI adjacent things, he was talking about how the brains obviously use these RNNs. These there's recurrence happening. There's this I always get tell me what's the difference between an RNN and a C? I get RNN and CNN confused. A convolutional versus recurrence. I guess recurrence to me feels like there's some kind of feedback loop. While convolutional, I don't really know what's
Right. So it's really interesting, actually, the history of these things, because some of the choices that were made architecturally for these different architectures, they were just because they had these constraints. They were living in a world where they didn't have a ton of data, and they didn't
in the
have
old times, in the before times,
in the before times, you couldn't just like push a button and then you spend several days figuring out your NVIDIA drivers situation. No, it was much more complicated even than that. I think that the AI apocalypse has no chance of happening anytime soon, just because driver issues
Driver
is
issues.
really the thing that they'll run into. Absolutely. So I'm not bitter. Not bitter.
Nice.
Anyways, more seriously, so CNNs are. So there are a few things which are really characteristics of CNNs. One is that you do the same operation over different areas of space. So that is the quote unquote convolution. So a convolution, refers to a mathematical operation in which you essentially like slide this operator, which is like this mixed multiplication and addition, over this two-dimensional or three-dimensional field. And so the convolution says basically take the same operation and apply it to different places in this image. The advantage of that compared to an arbitrarily connected neural network is that you have way less parameters, because when you say, what's going on here in the top left is the same as the thing that's happening in the bottom right, you've just removed, a degree of freedom in the way that you build your neural network. And that was historically very important in order to get these really good results. When back in the day, we're talking like 386 days, right? This is it was a long time ago, right? When they did this stuff. So I don't know if you remember the games that were there back then, but it wasn't like a paragon of
Didn't have the best graphics.
Yeah, exactly. Like think about like Super Mario Brothers versus like whatever's the big
Elder
big game
Scrolls.
these days.
I don't know, the kids, whatever the
Dark
Gen Zers
Souls
are playing. Yeah,
Dark Souls 7 or whatever it is.
Exactly. So it sounds like. Well,
Yeah.
thank you for the reminder there. Yeah, that CNNs are the things where you're taking some kind of like Gaussian blur, or whatever, or you're making some kind of thing, and you have an image, and you have your little 3x3, and you're kind of moving it across the whole image. And as you're saying, that's very helpful, because then you don't have to. You're saying, hey, we're just going to apply this same thing. We're gonna take this set of 9 pixels. We're gonna maybe even turn it into 1 pixel, and then we're gonna do that across the whole kind of thing. And then when you do that once, then you do it over and over and over again, and then you get some kind of output at the end where you say, oh, this is a cat or whatever. After you train the little square, the 3x3 and versus RNNs, which are the recurrence bit where you're trying to understand the time series thing, where you're trying to it was like the pre-transformer thing where you're trying to understand some kind of text, and you have to like look backwards, and you have to be like, what was said 2 minutes ago, or like backwards in the sentence, where you're like, was there a he there, or was it a she, or whatever? Should I use him? So okay, got it. Thank you for just in my mind I was like RNN and CNN, they're so similar. So back to the main.
Yeah, no, it's they're literally like one edit distance.
They're one edit distance as a simpleton like me, exactly. So back to this brains on demand, brains as a service thing. So tell me about. So I guess it might be actually helpful for the listeners to kind of imagine. I think there's this really brilliant idea that you have, which is we have a lot of, with generative AI, the supply of images is a lot. You can just like produce tons and tons of stuff, push it out there in the world. It's now, instead of a human needing to create it, nope, it's just like it's just being created at mass production. But the question is, what is the demand side? And so the demand is like, where will all these things live in the world? And I think that this great idea that you have is that there's, instead of like needing to test it and A/B test it on like, oh, is Rhys gonna like this redder image or this like bluer image? Instead, we can just like spin up these brains on demand and have them be the things that like do the testing to see which images will be more or less helpful. So kind of tell us more about like this like long-term future of how these brains on demand will be used from like a market perspective to like determine to do the testing before the humans need to, instead of having the humans as test subjects, we can just test it on the brains.
Oh yeah, absolutely. So I guess the picture that I paint in this blog post is that, eventually these in silico versions of the brain will be good enough to do practical things. They can be used wherever human perception might be used. For some applications, whether the CNN or your artificial neural network is aligned to a brain doesn't really matter. So I'll give you an example. If you're doing a self-driving car, there might be very good reasons why you don't want these two things to be aligned. Why? Because we know that humans have all of these issues, because they have these squishy brains, so they might not pay attention all the time. They have different resolution in the center of the eye versus the periphery, whereas for the car, maybe you want it to have high resolution in the periphery. So for some applications, whether your artificial neural network is really equivalent to the brain doesn't really matter, or doesn't matter as much. However, where it might matter is when it's applications in human health, or the person that's going to see the stuff that you're trying to make ultimately will be a human, because they're obviously like going to be very sensitive to stuff that humans are sensitive to, kind of by definition. So for these kinds of applications, I think that these artificial neural networks that we're building right now, which are aligned to human brains, are going to be absolutely important. And so they're kind of a baseline technology. And so I imagine a future in which you can download like this brain on demand in the same way that you can download like a transformer off of Hugging Face to do natural language processing. That'll be like neither near or there. Right now, it takes like a lot of resources in order to be able to do that. Maybe there's 100 people that know how to do it in the world. But you can imagine a future world in which, it's completely commoditized, and, there's a million people that, like the million people that have access to DALL-E 2 or Midjourney or Stable Diffusion.
Yeah, that's great. Yeah, it's like everybody right now we're quote unquote democratizing access to the creator tools, DALL-E, Stable Diffusion, etc. But in the future, and then we've also democratized access to the underlying infrastructure through downloading a transformer through Hugging Face. And then in the future, yeah, we're going to have democratized the access to these models of the brain, where you're like, hey, there's like, if you want to pretend, you want like you want a guy like Rhys, you want like a rich white guy straight in America, 31 years, like boom, like here, just like download him,
Oh,
so,
you're making it sound much worse than it's going to be. But
yeah, I guess it doesn't need to be based on like identities and stuff. And there'll be obviously there're going to be a lot of ethical and whatever issues around like thinking about how to like differentiate brains from each other. But I guess the crucial bit, and I just love what you talk about, how like some of the initial kickstart for this will be both health applications, but also I think like the advertising applications, or advertising, or just like media, where it's like being able to, and tell us a little bit more about like this A/B testing of like, instead of testing on humans, this like testing of on these brains on demand. So tell us a little bit more about that.
yeah, absolutely. So if we look at generative AI, because I think it really is like the kind of playbook for what might happen with brains on demand, what we've seen is that by and large, what they're used for, like some people use them for applications and creativity, and to make like art shows and all sorts of wacky stuff. But by and large, the biggest applications, the biggest money maker is going to be to create content that it's going to be used for advertising and for getting, eyeballs on people. And especially in places where people can't afford to have their own graphic designer or whatever. So if you're like under resourced, you're an SMB, small medium business, and you want to create content for your webpage or whatever, like having these tools available to you just makes it so much easier to be able to have like a nice graphic identity, get people into your store, and then sell your flowers or your or your baguettes or whatever it is that you sell. I think that we're going to see a lot of the same stuff for brains on demand. So the first thing to think about, I really do think that the end game is to think about human health, right? Because if we can figure out a way to have essentially what is an in silico version of the brain, then the obvious thing to do is to use that to create different kinds of quote unquote medications or different kinds of training regimens that allow a person to overcome either like some psychiatric problem, or maybe they're actually doing fine and they just want to improve their cognition along some axis, right? So enhancement of the well, if you will. So that's one way. But That's going to take a lot of time because there's regulations and, you have to go to clinical trials and FDA and blah, blah, blah. So that takes at least 7 years. At the very least, it's going to take 7 years. So we have to look first at consumer applications, which don't require all of this, medical testing. Those are the kinds of things that are going to create real opportunities in the marketplace. And so I think that advertising is probably like the number one case scenario here, where right now it's very difficult for the small guys, quote unquote, to compete in the marketplace, right? Because big companies just have access to marketing departments, even though they might fire them arbitrarily for some reason. Sorry, this is film at the time that there's many things happening on Twitter, so this is this is top of mind. But they might have marketing departments. They can have illustrators. They can have like they can have like statisticians that do A/B testing to figure out like which kinds of marketing materials or which organization of the web page creates the best the best outcomes for the company. But if you're a small fly by night startup and you have limited budget, like maybe you can't afford to do that. And so a lot of this stuff is done by field. And so I see that if you have under 100 employees, probably you don't have the statisticians on staff or the data scientists to really do very well-informed A/B testing, and you might not have either the traffic in order to do it. So what are you going to do? Like these bigger companies, they have the budget and they have the capability to optimize the heck out of everything, and you're just trying to compete. So I think that if we can bring that to these to small companies, to startups that are like really trying to innovate, and I think it could be really interesting because it gives them a fighting chance in this kind of fight for attention, if you will.
Yeah, it's interesting. I think it will be. I think it just feels like it's going to happen, and it feels like it's and it's interesting though, the thing about the consumer angle versus the health angle, where it's like the regulations on the health side are good, and it's also like it's kind of sad that like in the end, like we might want more of those. Like, oh, like let's like test out a bunch of different like mindfulness regimens or whatever, and see how those like impact these brains on demand. And like, oh wow, these ones are impacted positively. Oh great, let's like have let's like give people those apps or whatever. But it's just like there might be too much friction on the health side. And so what we do is then we go to the places where there's less friction, like on the consumer side. And so that's kind of just like the first start for a lot of these things, which is interesting. I want to, as we start to get into wrap mode here, tell me about like you're talking about how you're making a nomenclature for NeuroAI. What you're making a glossary, a bunch of words. Tell us about that process and how that's going.
Yeah, so I think that it's a big tent. NeuroAI encompasses a bunch of different practices, and it can be hard for even people in the field to agree that they're all talking about the same thing. And so I think that there's like really like two ways to map out this space, and there's kind of two axes that you care about. The first is, what's your home turf? So there's this principle in people who are translators, and by that I mean like literal language translators, that they should translate into their native language, right? So I'm French, I would do English to French, and presumably that would help like get the best possible outcomes. If you're quote unquote native in a language, or if your area of application is really thing X, that allows you to better understand the market conditions and to better understand the actual practice of implementing things in a way that can lead to positive outcomes. So some people are centered in AI, and other people are centered, their area of applications is neuro. And then the other axis is whether or not you are interested in NeuroAI because you think that you're motivated by curiosity, or you're motivated by applications. And so with that, you get like this two-axis kind of thing, where, in one corner, you can say like, I think that brains are really cool. I think like nobody's going to deny that brains are cool, but let's say that like that's your primary like ethical positions. And I am going to use AI-based tools in order to study the brain further and to further my understanding of this like incredibly mysterious thing that's all in our noggins, that is responsible for all emotions and everything that happens in our lives. On the other hand, other people might say, well, AI is useful in the sense that I think that AI is my home ground. I'm doing like production systems. I can inspire myself by things that are known in neuro in order to help alleviate the drudgery of human existence, of which there is much. And we've got everything in between. So that includes, so if you look at the whole spectrum of NeuroAI, that can include things like mining neuro to find new AI, using neuro data to realign existing AI so that they're more human-like. You can use AI as models of the brain, precisely do this kind of brains on demand thing that I've been thinking about. You can use AI models to really tune the next generation of brain-computer interfaces. We didn't have time to get into brain-computer interfaces, but it's definitely something I'm interested about. Or we can even use neuro approaches to investigate the current artificial neural networks as though we're doing the kinds of perception research that people have been doing for dozens of years now in neuroscience. So there's a big space, and I'm trying to put this all together and hopefully making a one-stop shop, a portal where people can get this information. Every time I talk to my statistician friends about that brains might be similar to AI, I get a lot of questions, and so I've decided to write it down, write down the answer.
So you can just send them one link, which is great. Well, I'm really excited for that. I mean, it sounds like it's a great. I love a good 2x2, and it makes sense that a NeuroAI is both on research, or sorry, is a neuron, the brain on one side, the neuroscience on one side, AI on the other side, and then the research and to applied. And you can always it's a cool thing because then like anybody in that field can kind of like look at that map, and then they're like, oh, cool, yeah, I'm an applied. I'm an industry kind of applied AI person. I can pull inspiration from any of the other three boxes. So that kind of makes sense.
And what is a map for? But to figure out where the stuff that is unmapped is, right? Yeah. If you got like a big spot, like, oh, maybe there's Greenland behind that. Who knows?
Yeah. That's funny. Yeah, and then I want to do one final question here, which is like a lightning version of overrated and underrated. So I'm just gonna say whether something, I'm gonna say a thing, and then you're gonna spend 15 seconds to say, hey, it's overrated or underrated, and here's one sentence on why. And so the first one, and talking about BCIs, is Neuralink. Do you think that's overrated or underrated?
I think it's about even. I think the technology is incredible. But the application area, it's a very small market, and the path to market is really tough.
Cool tech, but tough go to market. What about this is kind of a funny three-parter. What about EEG, fMRI, and PET scans?
PET is. I don't think that it's overrated because for studying the brain, it's pretty weak sauce. The quality of the images is very low, but it is good to measure these metabolic effects, and so it has a lot of applications actually in the clinic. So neither. fMRI still has a lot of fight within it. There's this research from Alex Huth at the University of Texas where they're able to decode people's silent speech. So in other words, like their like intent to speak, like even though they don't like actually like speak the thing, using fMRI. So it's really incredible stuff. That's also possible with MEG. EEG, I think, has to be very highly tuned for applications. People have tried over and over again to make it practical. It's a very mature technology. If it hasn't happened before, it's probably not going to happen now. So overrated.
Great. Throwing shade on EEG. Great. Beautiful. Well, thank you again, Patrick, for the chat today and for kind of, sharing this future about both, how we will eventually exist in this neuro AI future where these brains are on demand, and then kind of just doing the good work of like mapping that space. I think that's really important kind of field building. So thank you for that. For the listeners, definitely check out Patrick. Just a lot of cool writing on his website, xcorr.net. That's xcorr.net. So check that out, and then also Patrick's on Twitter at Patrick, that's Patrick, and then Mineault, French style, aka Mineault, Patrick Mineault on Twitter. Anything else you want to say to the listeners today, Patrick?
No, I mean, it was really great talking to you. Glad we have the chance to catch up, and hope to talk again sometime.
Yeah, I'll definitely, as you, I'm excited to see the, definitely please send me the, or CC me on Twitter or whatever, when you post the NeuroAI kind of 2x2 and the nomenclature market map. That seems amazing. And excited to stay in touch as this field emerges. So thank you everybody for listening, and goodbye. Thanks so much for listening today. If you liked the show, please give us a 5-star podcast review or subscribe on YouTube. And if you'd like to chat about this episode with a community of amazing, smart, ambitious, divergent people, come on by and join our Discord. You can find it at root.co. That's ROOTE.co. And then finally, if you'd like to contribute to these ideas being shared more widely in society, you can support the podcast production team at patreon.com/Rhys Lindmark. That's patreon.com/RHYSLINDMARK. Thanks, and see you here for the next episode. Bye.